essentially I want to talk about two methods because oh, this is so small. Yeah, this is better, I think. In fact, yeah, because I 2 days ago I didn't feel very well. I think I'm catching some kind of flu, so I didn't have time to tap everything. This is Lee. Who did the tapping? Yeah. So you have to be to tap those. Otherwise, I could have made it into the PDF file. Didn't feel very well. So just let's using this 1 hour to do the AOS and the Augmented Lagrangian. So we have been, you see, for a lot of the fast algorithms. Let's start so this is the Laplace equation for image processing. So for image processing, this is the most fundamental equation. So everything you start from here, and then you get more complicated things. So if you can't make this work, and then you can make the other work. So this is a fundamental solution, and mostly to avoid zero, you add the epsilon. So this epsilon will be defined somewhere. So that epsilon is mostly
here, in the middle.
In the middle.
Oh yeah, you define it this way. So this is mostly you try to solve such a kind of, and then once you have a small epsilon, this equation will not be generated, but you have a singularity where the function is and this is the gradient descent. So you add the t. This is gradient descent flow. So the most people even I still like this method is that you just use an explicit method. You have un plus 1 equal to un divided by delta t. This is approximately this one. And then here the divergence you just use a forward. Here you use a backward. Here you use some kind of average, that should be, or you can just easily even use forward, backward. So everything here becomes un. So this will be the explicit time marching. This is very easy. So the forward final difference is defined this way, and the backward is defined this way. So if you here use the forward, here you must use the backward, and that's always the duality. Always must the forward backward. So here you can use forward or just central anything. So mostly that doesn't seem to. So this is the method a lot of people use. The last year in Italy, so I first asked the student to implement this one, and then they implement the AOS. So most students did it. So they implement this one, then they implement AOS, and then compare, and they show me their code, and they test on gray image and color image. So here is the most simple way to solve it. Another way to solve it is essentially you do a linearization. So here you just linearize it from the previous equation, and then this becomes a linear equation. This becomes a linear equation. This equation you solve u and put it at un plus 1, put it here again. You can do this kind of such a kind of Picard equation. I think it was Vogel or Ullmann was the first one who was it Ullmann or Ullmann who first analyzed this one. They show the convergence. And so here essentially you see that the diffusion parameter is just the inverse of this one. So on the edge will be very, very small. In the region where it's very small, so this will be very, very large. So and then you have an anisotropic diffusion. So the method I'm going to talk. So after here, so therefore you can apply this multi-grid dominant composition on this equation, mix it somehow, and then you can make it fast solver. But in my opinion, you see that's not a real dominant composition, real multi-grid for this kind of problem. You can use the dominant composition multi-grid here, or even you can mix it in a very fancy way people don't notice. But however, that's not a real dominant composition, real multi-grid. So So a real dominant, real multiplication, you directly work on the nonlinear problem and take care of the special nature of this diffusion parameter. My favorite was the operator splitting, so so-called US methods and the Augmented Lagrangian. So the operator splitting US is can explain this way. So if E is a constant, you solve U equal to AT, so T starting from 0 goes to infinity, and then we know that this equation has a simple solution, right? Equal to ATU0. If A is bigger than 0, this equation is not stable because it explodes infinity very, very quickly. If A is less than 0, then it's stable, it decays to 0 very, very quickly. So this is, if you can split this A number into the sum of n numbers, right? Then it is equal to this one, and this is equal to this one. What does it mean? So it's what? So originally you solve A equation U equal to AT, T bigger equal to 0. And now you solve A equal to A1 plus A2 plus AMT. And then the solution, this solution equal the solution is equal to this one. So therefore you can see that essentially, so here you're starting to 0, assuming I just solve it T from 0 to a capital T. I just need that solution from and then what you can do, you first starting 0, solve to T with A1. And then you put this one as initial solution and solve it to T with A2. And then you do the same and put it here, solve it to here. And then you see that you solve the last one, so here is AM. Right. Because here is essentially is like EA1 TU0, EA2 TU0, and EAMT. So you first this one, solve this one, take it as an initial value, and then solve the second equation, and solve the third, solve the fourth. So this is essentially the meaning of this formula. So you never need to do this, right? No one is silly. If A is a constant, no one is silly to do this one, right? So otherwise, it's essentially you solve A1 equation and then put that initial value, and then you solve A2 equation, put the initial value, solve A3, and you do this n times, and then you get that equation. If A is a constant, no one would like to do that one. But this is just, if I explain this one in this way, you see, everyone understands. You see clearly this is correct. Yes, this is the case. But then, if A is an operator, or if A are matrices, so here let's replace this one by matrix, and then assuming this matrix can be decomposed into the sum of n matrices, and then you see U equal to AU equal to this one, and so that for the original problem, the solution will be this. And then for the subproblems, the solution will be this one. And here, e to the exponential of a matrix, you can explain it this way. Explain this way, right? So this will be the solution for this one if you replace this by A. So this will be a solution for this one if you replace those by AI. Matrix is AI. Once you come matrices, essentially we are solving a partial differential equation. So this is the operator splitting. So which means that this operator can be split into to m parts. If you split the number, those are exactly equal. If you split matrix, so this is the original problem. This is the split problem. But however, for matrices, it's not sure this is always equal. This is equal if all the submatrices are commuting. So which means that AI times AJ equal to arbitrary AJ times AI for arbitrary IJ from 0 to m. So here it is equal. So here is this one equal to this one only if all the submatrices commute. They commute with each other. If that's not correct, and then this formula is not correct. And then this formula is not correct anymore. So if this is correct, and that will be also very easy. So you first solve the first equation with A1 to here, and then solve the second equation with A2, and then solve the last equation AM. You solve it to there, put the initial value, solve for the initial value, and then you solve this one, right? But that is only correct if all those submatrices are commute. Also,
first equation should be U sub t equals AU, not AT.
Yeah, that's right, that's right. That's the typo. So here, so here should be AU. Yeah, here should be AU. Also here should be AU. Thank you. That's a typo. Right. So this is true if all the submatrices are commute. And this is stable if the matrix A is non-positive. If it's positive definite, if one of the eigenvalue is positive, and then the solution can export to infinity. If all the eigenvalue, none of them, especially assume A is symmetric, and then all the eigenvalue will be real numbers. And then if all the eigenvalues are less or equal to 0, and then this system will be stable. So if one of the eigenvalues is positive, and then this system may not be stable, right? So those are the two conditions to really, if you can really do this one. But this, for such a case, is very rare for real applications, especially for matrices corresponding to partial differential equation. This is seldom correct. If this is not correct, then how do you do it? And then you just use such kind of approximation. That E tau equal to 1 plus E tau inverse plus O tau square. This is simple Taylor expansion for tau bigger than 0. And for matrices, if AI is a symmetric positive definite, and this is an inverse matrix. So this is the inverse of the number, and this is also correct. So it depends on the smallest and largest eigenvalues. So this constant depends on the smallest and largest eigenvalue. But otherwise, you see this matrix is approximated by this matrix with O tau square when tau is very, very small. When tau is very, very small. And so using this formula, and then you see that if the tau is small, if the tau is small, we solve A tau equal to U0, and this can be approximated in each of them. You think that what was the formula? Yeah. So in that case, here t, we don't take a t very big, we take a t small. So here, this was approximated by the I minus AI inverse. So this approximate I minus inverse, and this one will approximate that one with O tau square. So that's what you want to try to do. And then you see that if you replace all the subnet by I minus E tau inverse 0, and this will approximate this solution by O tau square. So this means when tau is small, if you just invert it, those matrices, this will approximate that solution with something O tau square. O tau square. This is if you apply to the matrices. And so therefore, so what you can do that instead of doing this one, so what you can do now, so I want to solve from 0 to t. So here from 0 to t. So I divided this one to some small intervals. Each one has, so here is 1 tau, here is 2 tau, small tau, so here is n tau, so here is n plus 1 tau. So you apply this formula on each subinterval. So when tau is relatively small, so which means, so un plus 1 equal to I minus E tau inverse un. So you have a un here, so you have a un here, and then you get un plus 1, and then do the next one, and do the next one. So if this goes up, and then if you do such a thing, and then you can prove, so this one you get a un, and un you get it from previous one, and then un get un, and you go. So this you can prove that originally have O tau square, and due to the summation of the error, in fact, you still guarantee C tau. The summation of the error cancel one of the tau here. Otherwise, you preserve. So this is a C tau approximation. So which means when tau is very small, you still have a good approximation. You still have a good approximation. And so this is a code. This is one of the operator splitting ideas. Normally, you see this original operator A is very complicated, but each AI you split it such that it's very easy to solve. And then each subproblem is very easy to solve. And then that's making the whole problem easier to solve. Then that's the essential idea of operator splitting. You have many things packed together. If you put them together, it's so difficult to solve. But I just use you split one part, split another part, and solve each part, and then each part can be easy to solve. So this is the operator splitting. So this is called the sequential operator splitting, or so-called multiplicative operator splitting. It's in dominant composition. There's exactly corresponding. You have a multiplicative the overlapping dominant composition, you additive dominant. So the multiplicative in fact is exactly similar. You can interpret it in a similar way. And additive operator splitting. So E means additive operator splitting scheme. And this is you can write in such a way. So instead of using I plus M A tau, you put the M here. You put the M here, and then you divide it by M. And this you can see very clearly if you do the Taylor expansion. If you do the Taylor expansion, especially you see EAT is equal to 1 plus AT plus the remainder terms. And so you can easily see that if you put the M here, divided by M, and then you produce the O tau square approximation. O tau square approximation. So there you put the O tau square approximation if you do Taylor expansion. What's a good point? So what's a good point here? So here I'm very sorry. Here should be summation. So here should be summation. It's not multiplication. So essentially, yeah, so there should be summation. So E tau U0 is equal to M. So here is a summation I from 1 to M. I plus M tau AI U here inverse U0 plus O tau squared. So here is a summation instead of multiplication. That is the reason it's called additive operator splitting, because now you are adding instead of multiplying. If you use this one to solve that problem, and then how you solve it? Essentially, you still have a 0 to t, and you still divide it into many small intervals with tau, 2 tau. Originally, you see this problem, you solve to tau, you put the initial value and solve to tau, and then put the initial value. You need to do this one m times. M times. With this new scheme, so what you do, so essentially I solve A1 to tau, A2 to tau, A3 to all of them are starting with the same value, with the same UN. Right, because you sum together. You see, all of them solve simultaneously. But once you come to here, you do average. So you put all those m values together divided by m. So that's the difference. You solve each subproblem simultaneously, all starting with the same value. So everything starting with the same value. Yeah, everything starting with the same value. You solve all of them simultaneously. But then, yeah, but here you see that the time step is m tau instead of tau. You put the m down. Once you solve to here, and then you sum all those values together, dividing by m. And this was the new methods. Instead of solving one after another, you solve all of them simultaneously. So this is the so-called additive operator splitting. And so that's if you put the sum here. So, yeah. If you put the sum over there, and then that's a so-called additive operator splitting. Permanently memorized on the monitor. Yeah, so here, this is the additive operator splitting. You can also, this is also C-tone. This is also C-tone. So the additive operator splitting, which is similar to the dominant transition, so you have a better parallel property. And there's another thing that you see, all the directions are treated in the same manner. Mostly later, we are trying to show that if EI mostly is, we take it as a derivative in one direction. And so all the sub-operators are treated in the same way. So therefore, there is a symmetry with respect to the sub-operators. If you do the multiplicative, you don't have a symmetry. You can also add symmetry, but it's a different thing. So this is you have a better parallelization, and you have a symmetry with the sub-operators. That's the good point with the additive operator splitting. And that's for linear problems. For nonlinear problems, you can do the same. If those are nonlinear operators, so here's nonlinear operators, Fi, we just need to assume this nonlinear operator is maximum monotone. In fact, so it's tricky to analyze the operation. Yeah. So I think one sufficient condition, you assume each operator is maximum monotone, so which is corresponding to some convex problem. In fact, just if the sum is maximum monotone, it should be enough. Right? But for simplicity, you can just assume each of them maximum monotone. If a nonlinear operator, you can do the same. And in this way, you see the AOS scheme can be written in such a way. So here is essentially here become I minus, so therefore, right. Most probably everything here will be minus. Most probably everything here will be minus. But that, okay, there's a chance you see that here is the minus because I write the notes and it's not their fault, it's my fault. But if you apply this operator to such a nonlinear problem, so here is if you write it I minus it's I minus m tau, because if you write it this way, so you can see that u n plus I minus n, so equal to m tau ai. Here is u n plus I m. Plus m tau fi, here is plus un. So if you move this one to here, I get I minus m tau fi. So this is a nonlinear operator. So un plus im tilde equal to un plus m tau fi. So here is minus. Most probably I could have made a mistake, so here should be everything should be minus. Right. So in any case, so this additive operator splitting applied to this nonlinear operator is essentially to solve this one. So you always start from un, you solve m subproblem simultaneously. This is nonlinear, and then you average with m 1 over m. So you solve those problems simultaneously with step m tau, and then you do average. So this is the so-called I can send this logic to you. So I will correct those things can correct. Maybe I can even, yeah, because I don't have all your emails, I can put it here after a few days, next week or something. I can put it here. Maybe, yeah, if you put it here, so because this folder is not indexed. If you don't know the file name, you cannot get it. Let's say maybe we put a Tai 2Z. Right, so this is like a little bit new one, so I will put, so let's agree, right? So if you apply that additive operator splitting to such a nonlinear problem, so this will be the scheme. You start from a U0 here, each point, and then you solve M problem with M top, you average, and then put the value here, and you do the same, continue. And so this is the AOS scheme for a nonlinear problem. Now we see that how can we apply it to the ROF model? The ROF model, you solve UT equal to this one minus, and so you need to split into, so this is in 2D, we need to split it into two operators. So one is A1, another is A2, so here we split into F1, F2. So you split the operators. So here will be only the derivative with the x direction, here will be only the derivative with the y direction. So this operator only involves the x direction derivative. This operator only involves the derivative with the y direction. So this is how you split the two operators, F1, F2. And so therefore, if you use the AOS scheme, you need to solve two equations. One is like a u tilde n half 2 tau minus un u to the half x plus here. Even here we've done linearization. So here we don't use n half, but we can use the previous one. We do a simple linearization. Right? And this, if you write it down here, so here is this one, and you just put the ax as the inverse here. This is the ax, un, and this is a linear equation, right? Here with the uy. The uy direction is the same. You solve the u direction, uy. Here is also, or here is the, so you have the same kind of linear, right? After you solve both equations, you do an average of both equations at every nodal point. Look at this equation. Do you know how to solve it? We have many PD experts here. If you look at this equation, how do you solve it? Anyone can give great enough guess. How do you solve it? Who has been solving PDEs? Maybe we can guess how do you solve it. So in fact here, this AX is just this one. It also depends on Y. This also depends on Y. So this equation is especially if in the discretized case. So if this is image domain, so UX. So if this is a discretization, so and then you just replace this is a finite difference, and this is essentially an equation on such a line, on each line you have one direction, one equation. But those equations are independent of each other. On each line, you solve the equation. And this equation, essentially, if you discretize it, it becomes a 3 diagonal. And so those are three diagonal depends on the value of Ex, depends on this lambda, depends on tau, right? You get a three diagonal equation on each of those lines. And here, if you use a boundary condition, Ux equal to 0 here, Ux equal to 0 here on the two boundary, because the original equation has such a boundary condition. You see this one reducing at least 2 point equal to. So you apply Ux equal to 0 on both ends and solve such an equation. With Ex, Y are essentially, you see Ex, Y are the values are unknown here. So you just take the Ax value and then you get such a three diagonal matrix. So to solve the first part, you need to solve equation on each such a line. On each such a line is a three diagonal matrix. Three diagonal matrix, do you really need to invert the matrix? Sorry? No, how do you solve it? Professor Lee wants to give an answer.
Elimination or as a Fourier transform.
Yeah, so that's yeah. So three diagonal matrix, you can always do the code the Thomas average. You just do one down and then one up. So you don't need to do any inversion of the matrix. You just solve the Thomason. You go one sweep down, one sweep up. So it's like you have this is up. Those two matrices have x-plane solutions without invert anything. So the cost of this one is just some n number of multiplications, right? So therefore, to solve such an equation is very cheap, very cheap. You don't need to invert anything. You just once go down, once go up, you get the solution. So which means that on every line you solve such an equation. On every line, such a solved equation. And moreover, all of those lines can be solved in parallel. So they are independent of each other. And then for this equation, and then you need to solve an equation on such lines. From each line here, you need to solve equation, and here uy equal to 0, here uy equal to 0. You first solve in this direction, and then solve in this direction, and then each point you have two values, right? Each point you have two values, and you just do average of those two values, put it as a new value, and go to the next time step. So this is a so-called EOS scheme. You can do it for 2D, you can do it for 3D. You can use it for RF, you can use it for fourth order problem as well. People say it doesn't work for fourth order problem, I don't believe. And so this is a so-called EOS scheme for the RF model. And this, I think, was one of the quickest algorithms some years ago, especially Ron Kimo. Ron Kimo, he really had very compact implementation of this idea on MATLAB. He used it for surface processing a number of problems. He can make it very, very fast. So the cost per iteration is very little. However, the stability of this scheme is nearly the same as the implicit scheme. So you can have much larger time steps when you iterate. So compare with the explicit scheme, the very first explicit scheme. So this is goes to steady state much faster. So this is the so-called EOS scheme. It's cheap. It's stable. And so you nearly the same cost as the explicit scheme, but the convergence you get the implicit scheme, the convergence. So that's definitely something is no money for dinner. That's very good. That's the reason it's really very, very good. So this is the EOS scheme. So I think if you have some other problems, which may be difficult to have other fast algorithms, I think try the operator splitting is still one good choice. Try the operator splitting. And this method was made popular by Xue-Cheng in a paper by Xue-Cheng, Romani, the third person, I can't remember. So they made it, they introduced image processing. Was popular for image processing for quite a number of years. Still many people use it now. But in fact, the algorithm was proposed in our paper in 80, it was 91 or 92. The Xue-Cheng paper was 98. So the same algorithm which was proposed in our paper. So our paper, I think, was published by Liu, Tamaki, I think it was a PAI, was published in 91. So the Xue-Cheng paper was published in 98. But we have a number of algorithms, so this is one of the algorithms. The Xue-Cheng paper was published in 98. I think still for a lot of image processing problem, if you cannot find any other fast algorithm, try with operator splitting. It's still a good choice. But even you see here, I tell you what's a secret. So you split into two operators. So here is you have an E1, you have an E2. You see, to solve E1, you just solve a lot of linear problem. To solve E2, you solve another one-dimensional problem. So each problem is easy to solve. So if you get another equation, another model, if you can split such that each problem can be solved by implicit methods, then that could be a good choice. That could be a good choice. And now we come to the dual algorithm. I think this is for some people maybe it's not new anymore, but maybe for some of you, right, it could be useful. But still, let's go through it. So the dual methods, this is following the Shambo's the derivation of the method. So you solve this RF, and then we use the fact that TV is a U divergence of P, such that P is less equal to 0, and P should be 0 on the boundary. Right? And this TV is a TV in this way. And this is linear in both, so this is quadratic in U, so you can do a min-max switch. You cannot always do min-max switch, but under some condition you can do min-max switch. So you do min-max switch, so therefore, so here is a P less than 1. P is a vector, less than 1 and U. So similarly, if a P is a fixed, if you minimize U, and here, you see P is a linear, P is a quadratic. So here is the solution of U, right? And U equal to minus lambda inverse divergence P plus minus U0 if a P is a fixed. Right, because here you get divergence P, here 2 cancel lambda U, that's exactly this one. So that's a minimizer if a P is a fixed, you get U. So you take lambda inverse here, so move everything to here, you get minus lambda inverse divergence plus U0. So that's a U, right? And then this disappear, you put this U into there, you get U0 minus alpha inverse divergence P, divergence UP, you put this U replaced by this one, right? And then you put a U minus U0, U minus U0 equal to lambda inverse here. You have a 1 lambda, you cancel, you have 1 lambda inverse here, right? And then you can see here you have a minus, and here you have a plus half. So those two cancel, just become 1 minus. And that's those two terms, and this term is the same. And then you can just take a lambda, and here you get 2. So this is very simple. And then you put this square, you get lambda inverse square. Originally there is a minus here, but then here is maximizing. But if you change it to minimizing and you take this plus, here become minus. And then you put a minus here, but then you put this square, you get lambda inverse square. And originally there is a minus here, but then here is maximizing. But if you change it to minimizing and you take this plus, here become minus. But if you change it to minimizing and you take this plus, here become minus. Here become Maris. And so therefore, you see that you are minimizing this one, you minimize this one. So here is some constant term. But here P should be less than 1. Here also U disappeared and completely become a minimization of the dup. And this dup is a quadratic minimization here, but there is a convex constant here. There is a convex constant here. Right. You see, this whole derivation is very, very easy. You get U here, and this is just elementary calculation. And then the original problem, so here you originally minimize U, and then it become minimization of the P vector such that you minimize this one. Especially, I think Professor Lee, so you have been working. So here is a div operator in dominant composition multigrid. So here is essentially is grad div problem. But then you have a constant. Most of the grad div problem you don't have a constant, but here you have a constant. So therefore, you see that the original RF model can be written as minimized divergence P minus lambda U0. You take this constant away, such that P minus 1 less equal to 0 everywhere. And then I think Shambo is trying to use Lagrangian. You try to impose this constraint and use Lagrangian. There must exist Lagrangian such that it is equal to 0. If P is active, this alpha shall be bigger than 0. If P is inactive, and then you are in the interior, so this term could already equal to 0. If you're not familiar with this part, you just admit it. So when it is active, this term will be 0. When it's not active, so therefore this plus Lagrangian equal to 0. So that's when it's active, this is not active. So in both cases, you can see that alpha equal to this one. Right? Because when it's active, you see you take alpha, move to here, alpha is positive, P norm is absolute is equal to 1. So here is L2 norm of, here is a constant, here is a scalar. So alpha always equal to this one. Why alpha always equal to this one? Because when it is not active, this is a 0, so alpha is a 0, this is equal, right? When this is not active, so here should be exactly not equal to 1, should be exactly less than 1. When it's not active, alpha equal to 0, and this also equal to 0, so therefore this equal to this one. When this is active, why these two are equal? And then you just look into this equation. You move this one to here, and so here is this is a vector. So this is divergence, and this is scalar, and you get gradient. This is vector. So this is the L2 norm of a vector. So you move this one to here, so which means and then you have a gradient, here divergence P, here lambda U0 equal to minus alpha P. So it is in vector, right? And then you take the L2 norm on both sides. So this norm equal to 1, this become alpha, and then you get alpha, right? So alpha equal to this one. So which means that when it is active, this is also correct. And then you just put this alpha back to here, and this is the equation, this is the nonlinear equation P should satisfy. P should be satisfied. And then Shambo just used a fixed point iteration to solve this equation. So the fixed point iteration he used is essentially you add the P minus tau. Here you see this. Even this part we use the Pn So this part use Pn, but just this linear part use Pn plus 1. So compare with the previous equation, is just adding this part, like adding a pt. Then, so here is the previous one, here is the previous one, here is the new one. It's a fixed point equation. Fixed point equation. And then if you move this part to here, and then you get explicit formula for Pn plus 1. So here is Pn 1 plus tau. So here is Pn plus tau. So this is the iterative method which was proposed in Shambo's paper. You get a simple fixed point equation compute P1. You can prove that when tau is less than 1 minus OH, and this iteration converges. This iteration converges. And moreover, this iteration is very cheap. P has two components. P has two components, P1, P2. You need to, so you also check on the boundary if you have some special. But in the interior, you should always update. So this is the formula which was proposed in the Shambo's paper. It's very easy to compute. Normally, just take if you use an X-split scheme for RF, it takes about number of thousands of iterations. So here you just take about maybe 100 or even below 100 iterations, most to make it work. And per iteration per cost, it's the same. It's the same. So therefore, this turns out to be very, very fast. Very, very fast. And this is the CGM. So mostly CGM was the C is the Chang, Tony Chang, G is the Galo, M is the Mulan. So the CGM. So essentially, what they try to do with that. So here is ROF. You see that the explicit scheme with gradient descent. Shambo's method is gradient descent on the due problem. Is on the due problem. So what they want to do that, if you try to use a Newton method to solve this problem, and then you plus U plus delta U, and you need to differentiate, and this is a Newton. If you want to solve Newton, so here you put the residue here, and here is the differentiation of this operator with U once more. Here is a Newton. It's a little bit complicated. But when they try the Newton directly on that model, it converts very, very slowly. That's due to the non-differentiability at the zero. So instead of you directly apply Newton to this algorithm, they introduce such a variable W equal to this one. So this is so W is the unit normal vector to the level curves. And so there's a very easy physical meaning. If you do this one, so this equation you put W, and the first equation become a linear equation. The second equation you just multiply here. This also look like a linear equation. This also look like a linear equation. In fact, if you apply this one to the Poisson equation, this is a mixed element method. But then you get the linear equation. So here disappear. Yeah, you don't have this. You get a linear equation. That's a mixed element method. But for this RF, this is one. And then if you apply Newton to this system, and this will be the equation for the corresponding Newton. If you apply Newton on this one, and really convert it very, very fast. Mostly it convert if you have a proper initial value, it converts in less than 10 iterations, 10 or 20 iterations. So this is really very, very fast. But in some sense, you see that this is again somehow you see here the P in Shambo's methods is exactly also this vector. In Shambo's methods, the P is also equal to gradient U. Why the P equal to gradient U divided by in Shambo's method? Because the Shambo method is essentially divergence equal to supreme P less than 1. So here U divergence P. This is correct if P equal to this one. Especially if U is gradient U is nowhere constant. You can prove that this vector achieved the supreme. So therefore you see P in Shenbou's method, P also equal to this one. So in the CTM methods, they explicitly introduce this one and solve Newton. So therefore I have a split Bergen somewhere, but I don't. So split Bergen also. So now if we look at Augmented Lagrangian, so we look at the Augmented Lagrangian. So Augmented Lagrangian is a general minimization method. So you minimize f(x), x under such a constraint. So the Lagrangian method is that you introduce Lagrangian multiplier and put this one here in min and max lambda. So therefore one of the saddle points will be a minimizer for this problem. How many of you have been learning Lagrangian methods? Huh?
Lot.
Huh? A lot, okay. So okay, even if you will repeat. So the penalization is that you put here, you put a small penalization. And then when x goes to 0, the minimizer of this problem is getting closer to the original one. So Augmented Lagrangian is you combine those two. So you have a Lagrangian here, you also have a penalization. But due to the Lagrangian term, mostly you don't need the C to go to infinity. Just C can be any constant, should be okay. But this will enhance the convexity of the subproblem. So this is the Augmented Lagrangian. We have been talking quite a lot even in the last few lectures. So the RF, if you use Augmented Lagrangian, so the RF is a minimized total variation. If P equal the gradient U, so the RF can be written in such a way. Can be written as such a minimization problem. And so therefore, if you use Augmented Lagrangian, x equal to UP, h equal to this one, and then if you use Augmented Lagrangian, you get a mu, so you get p. So here is the Lagrangian term. Here is the penalization. So this will be Augmented Lagrangian for such an equation. For the new formulation of the RF model. Yeah. And this is Augmented Lagrangian. And so therefore the U minimization, U is quadratic, U minimization you will get such an equation. U minimization. So if you minimize the U, so U is quadratic, so you get lambda U minus U0. So here the U is a linear, you get divergence become omega. So here quadratic, you get here's a gradient, divergence, you get a Laplacian. So therefore, here is a U equation. The P equation, so here you have a PL2 linear quadratic. So therefore P equation, and you have an equation. So if a P is a non-zero, and that will be this will be equation. But P is a 0, so this is not valid equation. And the last equation becomes this one. So if you use Augmented Lagrangian, so here are the saddle point must satisfy those three equations. We can see that how can you recover the Shenbou's method from those Augmented Lagrangian? First, we notice that P equal to gradient U, so this disappear. The penalization term, this disappear. So the first equation just becomes lambda U minus divergence equal to 0. And this equation becomes, because P equal to gradient U, you have gradient U, gradient plus mu equal to here, right? So if you put this one into the first two equations, and you get this one, right? And from the first equation, you get exactly this Shenbou's formula. So U just exactly, that's the same as the Shenbou's formula. Yeah, and the second equation, if you just multiply to here, you get gradient U equal to mu equal to this one. But however, mu to this one, so you put the mu here. So you can see this is exactly Shenbou's algorithm, right? Shenbou's algorithm. So, but what we do, so here we have we have three variables. And you have mu is a Shenbou's P. So that mu is a Shenbou's P. So the Lagrangian multiplier is a Shenbou's P. And our P is equal to the gradient. Our P is equal to the gradient. Sorry? Huh?
U equals negative minus 1.
Lambda. Mu is a
So
vector.
that mu equals to P, right?
Well, equal to negative. Right. Yes, you are right. Very good. Yeah. So essentially, you see, our Lagrangian multiplier is that one. So this shows another way. You see, how do you get the Shambles algorithm? I think in another slides I will show you. See, this is if you just take a C equal to 1, that's a Xue-Cheng. Xue-Cheng is just the same algorithm if you put C equal to 1. So this is a connection. Also CGM. So CGM, you can see that CGM is essentially those two equations produce a CGM. Just multiply it here, and that's a CGM. But you don't solve this one. You use Newton method to solve this one. That's essentially CGM. So this is offer a way to solve. To extend the Shambles algorithm and the CGM and the number of algorithms. If you do this one using the Lagrangian interpretation, you can easily extend it to a number of problems. You can easily extend it to color image with a color TV. You can easily extend it to higher order methods. So this is a good point to use this observation to find this connection. So we are not claiming the other method is a special case of our method, of the Augmented Lagrangian. But we're just trying to show that there is such a connection. If you use this connection, if you use the Augmented Lagrangian, you can easily extend those methods to a larger number of problems. So therefore, this was first published in a paper by Tai Wu. I think SSVM, this is proceeding 01, and then another paper by Wu and Tai. So this is SIM imaging. I think this is I can't remember. This is yeah. So there is all those things are explained in the paper here in this paper. Also, I think there is another by KMRS, and there is a different. There is a very. So here he was relating quite a number of methods like Douglas rich food and different things. There is also SETZER, SETZER. So this is also SSVM09 in the same proceeding. So here is trying to observe relationship between Augmented Lagrangian, Douglas rich food, and the split-Bergman. So using this observation, you can really extend it to quite a larger number of problems. Also, I think our last Thursday, you were talking about using this one for compressive sensing. So in the case of compressive sensing, I think the relationship between Augmented Lagrangian and the split-Bergman was mentioned in the paper by Untitled and two other people. But for ROF model, or for a more completed picture of the relationship of the different methods, I think those few papers there is much more explanation and connections and extension. And also I think that this our paper really makes a very clear explanation connection. And if you read it, you can also see that how can you extend it for other problems. Also, just in that paper, we extend the CGM to color image, to higher order methods, fourth order methods. We extend Shambles methods to higher order methods, also to color TV. So this is. So hope we don't give impressions. We are saying that the other one's method is a special case of this one, but just by following this connection, you easily see how can you extend these methods to different things. So therefore, why this method is very fast. So here we need to solve a Poisson equation for U. We need to solve a Poisson equation. Mostly for image processing, the image domain is always square. The mesh is always uniform, and this is something we must utilize. This is different from elasticity. This is different from CFD, computational fluid dynamics. Image processing, the domain is always a square, the mesh is always uniform. This is something you should use. And mostly you're not allowed to do a local refinement. So what you compute on that mesh is what people should use for the image. So therefore, one way to utilize this one, you can really use it to solve this Poisson equation. You can use FFT or you can use EOS. So like use EOS here. Also another way, maybe you can use a dominant composition or multi-grid, but just do a few iterations, 2-3 iterations. And then these will be very cheap to solve. Very cheap to solve. Here is a solving of the P. So P, here is a L1 norm, here is a linear, here is a quadratic. And this should give you a shrinkage operator. This should give you a shrinkage operator. So essentially, here should be square. So here we should square norm. So you have a L1 norm. Here's a norm power 1. Here is a norm power 2. And these give you a shrinkage operator. So even you see how can you? Yeah. So there are different ways to derive this one, and then one easy way to derive this one is very easy. So why you minimize? That's also yesterday I talked with Professor Lee. So if you use you see like a multi-grid for the TV norm, and you need to minimize something similar like here. And this one has a shrinkage solution. Why? Because so Q, if a W is W0 is here, and then you draw a circle. You draw a circle here. And then you see Q to the distance W and the Q to the, so this distance should be in power 1, this distance should be power 2. And you can show that if a Q is outside this circle, you cannot minimize this one. So the minimizer must be inside. And then assume, you see this is 1 Q, you just draw another circle, and then you can show that, you see that, so here you get Q star. So here you get Q star. Maybe, yeah, so I think I have this explanation on the next page. Yeah, so first you show that Q outside is impossible to minimize that. So we want to minimize Q plus a constant, so here Q minus W0 norm squared. So there's a tempo in the break. So we want to minimize this one. So first, the Q outside this circle, you can easily shoot it out. It cannot minimize because it's even bigger than just taking W, Q equal to W. You cannot minimize. So assume Q somewhere here, and then you can see, and you pick a Q star, which is this one. And then you see this one is longer than that one, right? That's the first equality. And this one is longer than this one. That's the second one. And then if you put those two together, so this one plot is longer than this one. So that means Q star has a smaller image. So that means that this Q star here has a smaller image. So that means if a Q should be minimizer, and then it must be on this line. So simply this geometry shows that. So that means you see Q must be on this line. And then if a Q is on that line, so therefore Q star must equal to beta W0, and this should be 0, 1, put it here. And this is for beta is just a quadratic. And quadratic you get the minimizer, and you see that the minimizer must be given by such a way. So this is a very elementary explanation. If you minimize a mixing of L1 and norm 1 power, norm 2 power, it turns out to be shrinkage. It turns out to be shrinkage. So if you have some beta power, and beta power, you can do similar geometrical interpretation. You can get similar shrinkage. Here you see that we have both are positive. So we have both are positive. Sometimes here maybe you need a negative. In fact, we encounter one case here. Negative, you can also get similar formulas. Similar formulas. So therefore, the second problem. So so essentially this minimization. So the first minimization you solve that. The second, this minimization, so here is a tempo minimization is square. This is a shrinkage, you get such a solution. So the first equation, FFT or OES, just one iteration of OES is very cheap, and this is very cheap. And so the overall algorithm is becoming very, very cheap. So you solve U by Laplacian, P by Schrank, updating by this one. So this is the first order of Lagrangian. That's become very, very fun. So now you see that we show you how do you, this was explained in this paper. So how do we use it to solve the second order? So here is a Hess matrix. This is L1 of Hess matrix. So this we say you can, also she was talking, you can avoid staircasing. How do you use Lagrangian? Essentially you introduce a new variable. This matrix equal to du squared. So H equal to this U matrix, XX, UX, Y, UYX, UYY. You introduce, and so here is L1 of this matrix. And you put it here, and you put this as a constant. So here is a matrix. So matrix dot product with another matrix. Here is a matrix L1 norm square. And then in this way, you can use the same, you see, just using the same way. So you minimize U. So here you get U. So here is just the Hess matrix. This is a constant. Here you get du. Here this is table. This should be outside. So that one should be C d squared. Here is H minus du. So therefore, this d squared to d squared. This produces a fourth order partial differential equation. Produce a fourth order partial differential equation on U. Fourth order, second order, you can solve the FFT. There's no difference. So this here you can still solve the FFT. And the edge, you see still edge, you minimize a metric 1 norm. So here is metric 2 norm. So here is metric linear, you still get the shrinkage. And then here you do an updated Lagrangian. So the only thing different is here. Right? You can use the same thing to do this one. So therefore, if you use this one for the fourth order problem, it's very, very fun. I think this is also very much related to what you are doing. So I think maybe even this idea has been extended by a number of people now. So here is a du is a Hess matrix. The d5 is and then du here 2 is that should produce a fourth order PDE. Fourth order PDE. Yeah, so a lot of things that explain this paper. So now you see that if you use it for elasticas. So if you use elasticas and then and you just follow a similar idea, the elasticas, this is really difficult to solve. So we feel really happy. We felt really happy if we could use Lagrangian. So essentially for this one, we use a P equal to this one, and then A equal to this one. So therefore you have UPN, you get E divergence, you get P. And so instead of is your origin just have 1, and now we have this is unit vector, and you do this one, and you see that this constraint is easy. How do you deal with this constraint? So this constraint you just multiply n to here, but this constraint you see you have 2 terms multiplied together. This is it's not pleasant. It's not pleasant. But then we did a trick. So in fact, this one is equivalent to this one plus this one. It's very easy to, so therefore, yeah, let's just quickly explain this one. So therefore, the original constant is that we try to impose u n equal to p. And this is not pleasant. So what we do that, we found that this constant is equivalent to this one, so which is p equal to n inner product is p if you assume n is less than 1. Why this is equal? Because you use the, so here you use a Holder, is called Holder or Cauchy-Schwarz, and this is less than n less than p. But this is less than 1, so this is less than p, right? And so therefore you see that p less than p, the only thing happens is everywhere equality. If the equality, and then it only correct if p equal, if n equal to p. If the equality should happen, this must be, and this is equivalent. So therefore, you see, we found that this constraint is equivalent to those two constraints, but this constraint is very easy to do. Because here, if you hold one fix, it's a linear with the other one, and here is just a one norm. So we play such a trick, and then you see we impose those two constraints and use Augmented Lagrangian, and then you get to something which is very, very easy to solve. Which is very, very easy to solve. So here is the constraint for this one, here is the constraint, but we don't put the square. Why we don't put square? Because this less than one, this term is always positive. So there's no need to put the square. Here we put the square here. But if you do this one, each subproblem is that either you solve a linear second order equation, or you do a shrinkage. So each subproblem is, yeah. So therefore, in this way, we get very, very fast algorithm for elastic cost. And also, you see, during the last two lectures, you guys, we have several of the algorithms, several algorithms we have been using Augmented Lagrangian. And so there we have the constant, even to the max floor thing. So we have a divergence, we have a flow conservation, right? We have this divergence. We have a divergence of P plus PS minus PT. So this is equal to 0. We have been already using Augmented Lagrangian to deal with such a constraint. All right. So therefore, so I want to say, you see, the operator splitting is a very good idea. The Augmented Lagrangian is another very good idea. So those works for very general problems. So I'm not saying is like a Shenbos method is not good or the CGM is not good, but those methods are specially designed for one problem. Especially if like a Shenbos, if you use his derivation, if that derivation only works for RF. If you want to do another problem, at least in that formulation, it doesn't work out. Even you put the kernel, if you try to use it for deep learning, it doesn't work. But like Augmented Lagrangian operator splitting, so these are very general methods. They work for more general things. So there is hope you can really extend those ideas for other models. It turns out very, very fast. You see, like this algorithm, it just turns out very, very quick. So we have been testing for the elastic cost. Right. Yeah. So I hope you see at least you capture what's operator splitting. What are the? So most of these algorithms are related to the due. So there is a due involved, and mostly those due has a physical meaning. Our due, yeah, we have it clear. And so our due also has a physical meaning. Also for this one, you see the due was just the count. The due is just a count. So yeah, so that. So I hope you have a chance, especially Augmented Lagrangian. It seems for a lot of models use Augmented Lagrangian. It's an easy way to get something which is fast. It's an easy way. The people have been using for compression something for these higher order, but they also use for fingerprint and for everything. It turns out become quite general. A lot of people are starting to use Augmented Lagrangian. I think in some sense, I think everything you can do with Shenbos due, most probably you can do Augmented Lagrangian, and vice versa. What we can do here, we can analyze there. But maybe Augmented Lagrangian is more straightforward, much easier for people to extend it. So I think I want to stop here. So I should really, some professor need to organize this seminar. I've been using a lot of time to prepare the things, but at the same time, I'm very happy. I was able to pass some of the things we have learned to you, so you don't need to dig around in the literature. So you can start from here and do some better research, and especially Korea is very, very advanced with technology, multimedia technology. So I believe they have a lot of demand for image processing computation. So Korea is a really country such a thing should use. So I really hope you see use it in your future. I thank you for coming here for all those 5 times, and really enjoy the time here. Thank you.